Good day. In this simulation, I'm going to show you how large sample properties work in the context of ordinary least squares regression. The idea here is that as you increase the sample size, you're getting a more and more consistent, or you're getting a more and more efficient estimates, right? So you're getting closer and closer to normality. So that's your large sample that's your large sample properties that covers your central limit theorem. So as your sample size goes large, your distribution becomes closer and closer to the normal distribution. And in the case of OLS, the message here is that when you increase your sample size, your estimates becomes closer and closer and closer, asymptotically closer to the true value of your population parameters. I'm going to show that using a simulation, repeated running of OLS using R. So we're going to use the same parameters that we have used in the previous video to show you how omission of a relevant variable or the inclusion of irrelevant variable affects the results of your regression. Now let me just input some of the components here. So you have library mass. This mass package allows me to generate random variables drawn from the normal distribution. And let me also include the Ggplot2 package to plot the estimates from the Monte Carlo simulation that we'll be doing. And let me also construct here, now after invoking those packages, let me construct the covariance matrix for our two independent variables, which is x1 and x2. So I'm going to show you two cases here. In this case, we have a correctly specified model, right? And we'll see how the distribution of the estimates converge towards a normal distribution. Of course, we're assuming that this is normally distributed, but I'm going to show you how those estimates converge closer and closer, more precisely nearer towards the true population value of your parameter. In another case, I'm going to show what happens if you omit a relevant variable in your regression model. So technically speaking, while large sample properties are beneficial, and in essence, it's telling you that when you're running an OLS regression, you should be including as much sample, as many sample observations as possible. It will not cure the problem of omitted variable bias. And in fact, it could even worsen in the case of omitted variable bias. Okay, so let me reconstruct my covariance matrix here. For now, let's assume that we have this covariance matrix between the two, and this will be important later. So you have n row, 2, you have 2, you have a, let's include the first elements for the covariance matrix. We have 1, you have for this second column, you have 0.3. Let's make it uniformly, let's treat it uniformly at 0.6. And you have your second row, it's also 0.6, and your last element, which is equal to 1. Okay, so that's your covariance matrix. Okay, so let's start off with the first simulation, basically the first set of results. Now, the idea here is that I'm going to show you how the distribution of these estimates would vary depending on the sample size that you indicate in your least squares regression. Okay, so let's start off with let's name it model 1, right, with fewer observations. And let me construct the simulation program by setting up the independent variables first. So you have MV R norm. And let's start off with a sample size of 10, very few observations. Now you have a very few set of observations. and you have your mean. Let's assume that the mean or mu for these, for both of these variables is equal to 0 and 0. And let's obtain the sigma or the correlation matrix, and that's given by matrix A. Now, just a side note, what I really enjoy about doing simulations in R is that it's more intuitive. Of course, you can do this in Stata. You'll just have to create the program, necessary program that will capture the model. You have seen that in the other videos, but here it's more intuitive, and you don't actually need to create a data frame in order for your simulations to run. It's basically stored as an object in your R environment. It's a really cool feature. So let me define, so now that we have a matrix, basically this is a matrix X, and let's extract the individual variables. So you have X1, and that's basically column 1 of matrix X, and you have column 2 for X2. So those are your independent variables. Now let's construct the model that we're going to simulate. So you have M1. Let's construct the function. Now in this function, we're going to define the parameters. We start off with the number of observations. We set it at 10. Let's set the intercept of your data generating process for the dependent variable y at 10. Let's set the intercept for x1 at 0.5, and let's set the intercept of 2 at 0.3. Now in other applications, you can manually set the variance or the standard error, but we'll just use the default and assume that the standard error, the standard deviation of your error term will be set at 1. Okay, so these are the parameters, and let's define the program now. Let's define the function. So the function here would be y. Okay. So beta naught plus beta 1 times x1. Of course, you can manually, you can skip this part, okay, and you just input the actual numbers for your data generating process. 2 times x2 plus the error term, which is we assume to be normal, with number of observations equal to 10 and mean of 0. So after defining this data generating process, we create the model, we create the regression model, name it y hat, and that y hat is basically the regression of y on x1 plus x2. I'm pretty sure you can come up with a more efficient program, right? There are a lot of tutorials out there that maybe can shorten the process, but I believe that this is one of the quickest way to create a simulation program. And let's add the coef function y hat to allow us to easily extract the results. Okay. So that would be our first model. It will be our first model. Okay. And we can run the simulation. Okay. You can run the simulation and extract the results. So you have sims, let's name it sims, replicate, right? Over, say, 1,000 times. We'll do the regression 1,000 times, and let's call the function M1. Let's call the function M1 to do, which will be done 1,000 times over. And let's extract the results for X1. Let's name it res1. Of course, you can also do it for variable 2, for X2, but that's fine. For simplicity, let's just focus on X1. So let's name the coefficient estimates for X1 as res1, and we extract it from the object sims, right? It's in row 2, and let's get all of those columns, right? The thing is, when you run the simulation command, which we will see later, it will generate sort of a matrix whose rows are the estimates, so beta naught, beta 1, beta 2, and the columns will be the replications, right? So there'll be 1,000 columns and 3 rows. We just wanted to focus on row 2, which is the coefficient of x1. Okay. So let me just copy this, and rename the second part as model 2. Now I'm going to tweak things for model 2 and replace the sample size, make it a little larger. Let's say, let's make it 1,000 observations this time. Let's make it 1,000 observations. Let's make it 1,000 observations, right? And rename things. The parameters are still the same. We're still gunning for an OLS estimate that should be close to around 0.5 because that's the true population parameter value. Okay, so with all things fixed, let's rename this. Let's rename the second results, the second set of estimates as res2. Okay, to indicate model 2 with 1,000 observations. And let me copy this. Copy this and do the same thing. Rename this as model 3. And change a lot of stuff here. But now we're going to use 100,000. Let's use 100,000 observations. Okay. So yeah, we have 100,000 observations. Okay, 100,000. Right. But of course, the number of simulations will still be the same. Okay. The only thing that's changing here is the sample size for each of the model. Okay, let's rename this as res. Okay. So let's run the first part. Let's run this first model first. Okay. So this now contains the results for res1, or let's look at, maybe you're interested in, let's take a look at sims. So this is what I'm telling earlier, that sims, the resulting object for after the simulation will be a matrix whose columns are the number of iterations or number of times that the OLS program, the OLS model was estimated, and the rows will be the corresponding parameter estimates. You have the intercept, you have x1 and x2. We're just interested with x1. So we extracted here as, we extracted that as res1. Okay. And let's run the remaining set of lines, the remaining set of codes, in order for us to get the estimates, simulated estimates for model 2 and model 3. And I'm going to show you how different they are using a graph, using a plot. Okay, now the simulation is done. Now, if you have so many observations that you wanted to capture, it's really gonna take some time, right? It's really gonna take some time, especially now that the last model has 100,000 observations. It's definitely gonna take some time before you can get the results. Now, let's try to plot these results and see how asymptotics work. In essence, what I wanted to show here is that when you increase the sample size, you're getting a better and better distribution for your OLS estimator. It's meaning that it becomes tighter around the true population parameter or true population value of the parameter, and your distribution becomes less spread out, right, than the one with a smaller sample size. And in effect, in econometrics, when you have a smaller sample size, you should be expecting more noise. in your results. Whereas when you have a smaller, when you have a larger sample size, the noise diminishes, right? Your estimate becomes, the distribution of your estimates become less spread out, right? You'll be hitting the true population parameter closely than than the model that uses fewer samples. So let's plot that. Let's plot that using Ggplot. That's the reason why I included that library in this code. Okay, so let me type Ggplot. And let's plot the individual density. So you have the density function for the first estimate. So you have ES and will indicate which model. Let's start off with res1. That's the first model, right? And let's define the color name, right? This will be helpful for our legend later. So let's name it M1. So we're referencing to these. We're referencing to this plot as M1, which we will use later. Right? Let's define the next density for res2. Let's name it model to M2. Right? Let's name this M3 for res3. Okay. And let's create a vertical line just to mark the true value of the population coefficient of x1, which is at 0.5. So that would be x-intercept 0.5. Let's just make it thin. Let's make it size. Make it size 0.2. And let's indicate that the line type is dashed. Now, here's where we're going to define our legend, right? Of course, we need a legend for these density plots. So we have scale, color, manual. You're telling R that you're setting the color scale manually, right? Let's name the legend models, right? Next, let's indicate the colors for each model by typing values. And that contains 3. That should contain 3 elements. So you have the color for the first model, the second, and the third one, right? So let's select the color for M1. Let's make it red. Let's select the color for M2. Let's make it blue. Let's select the color for M3. Let's make it black. Okay. Of course, we need labels. We need labels for the keys, for the legend keys. So we have labels. We have labels, and this should also contain 3 elements. That's gonna be n. How many observations? We used 10 in the first run. Okay. The next one would be 1,000 observations. So let's name it as 1,000. And the next one would be 100,000. 100,000. Okay. Okay, so that should set it. And let me just add one key feature here. And I just wanted my Ggplot to be a little plain, so I wanted to have this theme, no panel grid. So I don't want any grids in my graph. The default here is that it has grids. So I wanted to eliminate that by typing element blank. I also don't want my any background, colored background. So I'll just type panel background element blank. Okay. And I want my axis lines to be black. So I'll type my axis line, element line, and set the color to black. Okay, and let's generate the plots. Okay. No, I think 10 observations might be a little too few. So let me just correct that. All right, so I think that's much better. So I replaced the third model with 10,000 observations instead of the usual 100,000 that I use, because it becomes really, really close to the population parameter, which is marked by our dashed vertical line here. So notice that when your sample size is small, it's really spread out, right? That's given by the red line. But as your sample size increases, it becomes tighter around 0.5. It becomes tighter around the true population value of 0.5. And that actually improves significantly when you increase the sample from 10,000 to 100,000 observations. So the story here is that when your model is correctly specified, and that's the primary story here, your model should be correctly specified. And when your model is correctly specified, you're better off using as many observations as you can, right? Because as you have seen in this result, as you have seen in this graph, it becomes more precise, right? You're hitting the true population value with minimal spread, in contrast to the model with the fewer observations. Now, let me emphasize here the fact that your model should be correctly specified, right? Because if your model is not correctly specified, large sample properties cannot be invoked. You cannot call on asymptotic normality. You cannot call on the asymptotics of OLS. You cannot conclude, you cannot just presume that the distribution will be as close to the true population distribution of your model if your regression, if your econometric model is not correctly specified. So let me emphasize it here. We have assumed that there is a correlation, right? We have assumed that there is a correlation between x1 and x2. Now, let me tweak this model this time. Retain the same data generating process for y, meaning y is still determined by x1 and x2 at the population level. But let's suppose that because of some practical reason, you're not able to collect x2. In other words, you omit x2. You weren't able to include that in your econometric estimation. Then of course, x1 will then be correlated with your error term. So let's deliberately make that mistake of excluding x2 from the regression. And let's see what happens. Let's run the same estimation. Now, this is an interesting result, right? Notice how off the distribution is from the true population value, which is 0.5. So increasing the sample size didn't help. Of course, it decreased the spread of the distribution of your estimates for beta 1, but at the population level, it's still incorrect because it's not centered around the true population parameter, which is given by 0.5, right? It's very far off, right? It's far off from 0.5, which means that increasing the sample size won't really cure omitted variable bias. If your model is not correctly specified, then increasing the sample size won't really help. This is an interesting graph, as you can see here. I'm encouraging, basically what I'm saying here is that you need to use as much sample size as possible, but you should be able to specify your model correctly. In practical terms, how can you even say that your model is correct if you don't exactly know the true value of these parameters? Well, this is where your literature comes in. This is where the soundness of your conceptual framework comes in. If your conceptual framework is correctly specified, if it is largely based on the existing literature, if it reflects the stylized facts that has been estimated by several studies, then you would have an idea of what the correct what's the idea of what the correct value of your population parameter is. Take for instance, say a demand, say for instance a model that tries to capture the demand for a normal good, say bread. When the price of bread increases, so let's say that the demand for bread is set on the left-hand side. That's your outcome or dependent variable. Let's say that the price is your independent variable. Let's assume that OLS is the correct methodology for estimating a demand equation, because later on, when you try to read advanced topics in econometrics, you would see that your usual demand equations cannot easily be estimated by OLS. Otherwise, you will be committing a mistake of running endogeneity or committing endogeneity. But let's, for the meantime, assume that estimating a demand function is correct using OLS. Right? Since this is a demand equation, you know in theory that when the price of something increases, the demand for it decreases. Right? So if the price of bread increases, conceptually you know that the demand should decrease. Now, suppose that you have collected data of bread consumption and the price of bread for a given community, and you've run a regression analysis and you have observed that the coefficient for price is positive. That's already a red flag. Right? Doesn't definitely tell you that it's correct or not, but it definitely gives you a red flag, a signal that your estimate might be wrong, because it contradicts the existing theory. It contradicts your existing concept, your existing knowledge of what or of how demand should behave with respect to price, right? So that's how we know. That's basically how you know whether your estimate is correct or whether your estimate makes sense or not. Right? Increasing the sample size may help in precision. In terms of precision, it narrows down the standard errors of the estimates. Right? It makes you closer and closer to the true population distribution of your model. But if your model is not correctly specified, then it won't solve anything, as you have seen in this example. So that concludes our short video on OLS asymptotics. Of course, you can run this using Stata. You can run the same simulation using Stata. We just have to refer to our previous video on how to run simulations and tweak the lines a bit to account for different sample sizes.